your EMCS 3003. I already uploaded the materials at there. And look at the practical sheets. Go to the Google Classroom, GMCS 3003.
In this video,
Okay. I haven't uploaded the assignment yet. I'll upload it by this week. Here we have the lecture slide and practical sheets. And in this practical sheet we have 10 practicals there. But 1 and 2 is has been removed because it requires Amazon, AWS, and you have to pay. Last time it was free, but right now you have to pay. Actually, it's still free, but then in order to open an account, you need to have credit card. So I think this is because I believe some of you might not have the credit card number. Okay, so let's skip to go to P3. In fact, this Amazon is just to show you the clusters in Amazon that you can use for help. But for our course, you don't have to use this option. You can use Collab. Collab is provided by Google. Every one of us has an account, so we can use the resources there. But of course, if you don't have Google, you don't have a license, you don't have the package to use the cloud services. You can use some of the services. The one that I know we have the package for. Okay, there are 2 videos here. One of the video, which is good, we're going to do it maybe later, not now. But we have to configure first our IDE. Okay? And in this video, there is no speech there. It's just showing you how to navigate through Video Studio IDEs in order to get your setting correct. Okay. Okay. If you look at your desktop, you see 2. One is Visual Studio 2022, and the other one is Visual Studio Code. Okay, you click on the Visual Studio 2023. Visual Studio Code you can use, but you have to install C++ yourself. Okay, and a little bit more tedious. I suggest that you use Visual Studio 2022 because it comes with a C++ pre-installed. Okay, so double click on this, and please install this at home as well if you haven't installed yet. I believe all of you already because you have studied C++ in other courses, right? So you must have this already. And we're going to use that. You might be using 2019. You can upgrade it to 2022, which is the latest version at the moment. And I suggest that you install this because some of the OMP libraries has been updated in 2022. It is only available here, but it's not available in 2019. Okay, first, this video here, if you miss what I mentioned, or you go back home, you try and then you forget the steps, please watch this video. Okay, but now I'm going to live. Okay, there's a difference. The Visual 22, the interface is slightly different than what you see in the video, but it's more or less the same. You can probably guess where the option is. Okay. Okay, first you create the main project, and then you create Windows console. Okay, I suggest that you type in here. The reason is because the list here can be a long list, so the search for it is difficult. What we need is Windows console application, C++. Make sure that it's Windows console and its application. Click on it, and then click next. Okay. Next, you provide the project name. Let's call it Practical 3, or whatever name that you want. Click create, and here the target is Windows 11. Minimum is Windows 10. It's super version. Of course, if your Windows 10 is not upgraded yet, please upgrade to this version. Otherwise, you can use it. Click OK. Okay, if you want to go through this document, you can go through. Office will donate, close. And then check, make sure that you have this name. You have a new project there. Okay, like what normally we do, we want to find out the project that is created, which has a skeletal code in it. Is able to run. So what you need to do is just run local Windows debugger. Let's make sure that it's able to print this. If you're able to print, that means your project is all right. It's ready to program. You are ready to Okay, the first thing that we need is because the first part, Practical 3, is going to use OpenMP or OMP. There's an official website there. You go to the official website. There's all the resources and also some book references and video presentation. And I think some tutorials as well. You can check out. Let's say you don't know how to use them. As I highly suggest that you read this there's some exercises there as well, such as a try as well. Okay? There is hands-on and how to use some of the features or functions. Okay, or the barcodes that is provided by Okay. First exercise, question number 1. The solution actually given to you. Just ask you to try it out. In order to write this program, we use the IDE Visual Studio, but we have to do some configuration because we need this OMP library. Okay? You can see the top one there. Top one is telling C++. Please use this. Okay, please use this OMP library to do parallel computing. In order to allow Visual C++ to be able to use this library, you have to include the library. To include, right-click on this, the name of your project, Practical 3 in my case. You right-click on it, go to Properties down below, and this thing will pop up. And then you go to C++. C++. Okay. Drop down, menu, select the language. Under the language, go to open export. Click on yes. Okay. Now if you miss what I mentioned just now, you can watch this video. This video is the same thing just there. This video over here. I show you the steps as well, except that this one is 2019 if I'm not mistaken. Okay. But you can roughly guess where to find the option. Okay. If you miss what I mentioned just now. Okay, once you have selected yes, click OK. Right. Now you can go in and run the program. Here it's different from the video because this is the latest 2022 and they are using this Week01, which is Windows real-time. Windows real-time has all this. This one is to print the hello something just now, and we do not need it anymore, so we remove. Now for the rest, I suggest that you keep it because you need this init department to initialize the Windows real-time. If you remove it, you will not run. Okay, you just leave it there. Okay, now we can go ahead and try the program according to this. Okay, so we have to put the OMP header, and then inside of me, we have to put in this program OMP parameter. The first thing is you get the track ID. Okay, and I'll explain to you and also show you the result. What is this ID all about? And the idea is to get the track ID and print it out on the screen. Okay? So let's go ahead and run the program. We move to include here. And then run the program down below. So integer ID, get track number. Okay. If you see very line like this, it means that you can't find it, so something is wrong. So you have to spell correctly. You have to wait for a while for it to realize that this is the track. Okay, if you still see like this, it means you must have done it the wrong thing. You go and check. Go ahead to get track now. Correct? Go back to get track. So I'll make a mistake there. You should be go back to get track. Okay. So you wait for a while, if it turns to this, then it also corrects. Now, if we still see a very nice correct. If you see still very like that, it is because you forget to include the OIP. Okay? Or if you have already included, you still see wavy line there, is because you forget to tick this. Go to here, tick this. Okay? If you don't see the wavy line, that means you can recognize it, that means you are doing it correct. Okay, next, one thing that I missed here is the front mark. OMP parallel. Okay, once you put this, if it is a single line, you just need to do it this way. If it's just a single line. But if there's multiple lines, you have to put it into a block. This block must be encapsulated inside this opening brace and closing brace. Alright? And this brace cannot be put in here. You cannot put this brace here. Alright? Some of you I believe prefer to write like this or maybe like this, right? For this is okay, no problem. But this is not okay. For pragma, you have to put on the next line. You cannot put it this way. If you put it this way, you will get error. Alright? So you have to put on the next line. Okay? Once done, then we can print out. Hello. Here is D. Here is ID. And then next is row. And also D. And this person. Something like that. Right? Okay, so now you're ready to run the program. Run it. And you see some result. You will see error. It's not issues. Yes. result looks like this, and it's pretty ugly compared to what is shown here. The result here show very beautiful. In hello world, 1, 1, 0, 0, 2, 5, and all that. Let's study this one first. This is the output that we expect, but our output is very ugly. Your output might be ugly as well. Okay? But let me explain this one first. Okay, we expect to see this. The reason is because we print out hello world. Okay? This hello world is in a single line is because I don't put /10, right? So even though I print F twice, but the world will be on the same line because there's no /10. If there's a /10, this rule will be F1, right? Okay. But hello world, there's only one there. But how come our output has so many hello world? By right, it should be one, right? The reason is because of this OMP parallel. What we did there was we tell the Visual Studio, this should be executed by a number of threads. And this thread can be running on multiple cores. So let's say the CPU has 8 cores, then you utilize 8 cores. Okay? By default, on my system, this one by default on the lecturer will actually prepare this slide. Oh, sorry, this practical sheet. This system has 8 threads. On our system, we have 16 altogether, if I'm not mistaken. Yeah, 16, because the last number I see here is 15. 15 here, and we start from 0. Here we start from 0. That means we have 16 threads altogether. Okay? This program actually starts in our system. It starts 16 threads, and all the threads will run this. Okay, run this concurrently. So you see hello world appearing there. And in the program, each thread that runs this will get its own ID. Okay, the thread ID. So each one will have a unique ID, and it get printed out here. So thread 1 managed to print first. That's why hello world 1 appears. Thread 2 came later and able to print on the second line. And thread 3, which is number 2, able to print as well, is on the third line. And it's not in order. So it depends on who is faster. Okay? Now let's look at our result here. Our result is also the same thing. We try to print, but it's much more ugly than what we see just now. Because they're competing with one another. Okay, and this is the problem. This problem is called race condition. What you're seeing here is race condition. Race condition I'll cover in lecture 3, lecture 4. Okay, it's a problem. It's a big problem, right? And race condition is bad because it can make your system unstable. Okay, so what you see here is you're racing because everybody tries to compete to display on the same screen. Right? The multiple cores, they try to write. So thread number 1 managed to print hello world successfully without any problem. And then came thread number 8, also managed to print. But thread number 0, before it finished writing the word, thread 10, thread 4, thread 11, thread 13, thread 14, thread 14 managed to come. And then they start printing as well before it finished. That's why you see hello 10, hello 4, hello 11, hello 13, hello. But hello 14 managed to print off. And then hello thread 5 managed to come in and then write also hello 5. Then only thread 0 managed to complete here. Then thread 10 managed to complete here. Thread 4 also managed to complete here. Before thread 11 able to complete writing the word, thread 2 came and then right. So they are competing with one another, and every time you run, you see different results because they are not. The result will be always different, okay? Depending on who is faster. Okay? And this is pretty bad because we do not want this kind of thing because it's chaotic, right? So these are one problem that we're going to face, and there's a solution to this to overcome this reverse condition. Okay? But we will cover it later. At the moment, we just leave it first. leave it as it is. Okay, so that's the first exercise. If you manage to print out multiple hello world, then you have done the first parallel computing hello world. So have you tried? Is it okay? Try it. Okay? Okay, please follow because later on there's an exercise for you to do. Okay, the next topic we want to look at is to control the track data. So in the parallel region, this is the parallel region. This parallel region. There's a code inside there. There are two types of data. One type is called private, the other one is shared. Okay? Alright, so we have various ways to actually use the data. Okay, some of the data we want to share, some of the data we want it to be private. We don't want to share it. Okay? The shared data, of course, there's some communication that you want to pass on, then we should use the shared data. But if let's say the data, we want to use it just for that particular thread, it should be private. Okay? It cannot be touched by any other threads. So it should be categorized under private. So how do we declare shared and also private data? So let's look at the shared data first. And the shared data is written this way. You pull it outside the pragma, OMP parallel. Okay? You declare it just like the C++ declaration, integer x, and you initialize the 5. Now, inside here, if you use this x data is actually shared data. And in this case here, let's try to run this program to see the result. Okay, to proceed on, I suggest that we organize our code a little bit. I know that some of you tend to actually create a new project. It can be quite slow. And also, if you have multiple projects, you don't want to have so many here. And also, some of you will just delete it and then override the new program, right? And now you don't have the program, whatever program that you're going to resolve on. So I suggest you do this. You create a function, and then you encapsulate all this inside the function. Okay, let's call this exercise. Exercise 0. You take say nothing, and you returns nothing, void. Then you put your program in there. Okay, so that is done. Then you can copy this and then paste it here. So by doing this, now I can just call this function and then you execute whatever that we have done just now. You still get the same result. Okay, sometimes when you run, you see that it stalls like this, right? I'm not sure what happened. It means that the system has already stalled. You just close it, and then run again. And run again. To release from the stall. Alright? Okay, next we want to do this exercise. Integer x 5, and then we increment the x, and then we print out the result. So let's try that. Void. Let's call exercise 2. Sorry, exercise 1. And we this one to 1. And this one is 2. Plus here 1. And 2. Okay, integer x equals to 5. And then comma when p parallel. And here x equals to x plus 1, which is basically x plus plus, and then print that. Okay, and the shared data is okay. Now you can actually run exercise 1 and exercise 2, but of course this will use up a print out all the garbage you want to see, right? You can actually comment it out. Anytime you need it back to run the exercise, then you open the comment and then uncomment and comment this. Okay? So this will make your programming experience better. Okay? So that you can look at any result that you want or suppress any exercise that you don't want. So you run a program and now you get some result. Okay? The result right now, they got printed out quite nice. Not sure now why it's nice, because I expect it to be also in the race condition to happen again. So shared, and let's look at the result there. Okay, look at the program as well. Program next to it. Here we start with x equals to 5. And before we print, we increment the x first. So you see inside there, the minimum is 6, right? Because we start with 5, we increment first before we print. So share is 6. Then the next step comes in, because we run it 6, and then you increment, becomes 7. And then you print out, becomes 7. Right? Because this data x is shared, that's why whoever increment it, the other thread will see that change. Okay? So when the other thread that print, before you print, you also increment. And when you increment, the next thread that comes in to grab that x, you will see a different number, an incremented number. That's why that number is unique as well. Okay? Because it starts on 6, you end at 1, because I have 16 threads over there. Okay, so you should see this result, and you can see that x is shared. Okay, it's shared on all the threads. But how do we make it private? Okay, let's look at the next one. Okay, how do you make it private? We make it private by, there are 2 ways. One way is to declare it in subject. And also, the other way is to use the keyword called private. Okay? So there are 2 ways to do it. One is to use this declaration, which is inside this block. Okay? This code block. Okay, let's try that. I'm going to use this back, and let's call it exercise 2. Here, I have integer x again, and x is assigned to 3. Okay? And here, when I print it out, I make some changes here. Here, there's no plus here. Let's try the plus basic. I want to check if, let's say, I print and then I increment. Or maybe I increment first, then I print. Let's increment first and print. I want to see if this is really shared. If it is really shared, then whichever thread has come in, you see the latest x, and then you print the incremented value, right? So we see some result, the same result as just now. Okay, if let's say it's shared. If it is not shared, then you will see a number 4 here, because 3, after 3 is plus is 4, right? So we get to print out 4. Let's run the program. For that, get this exercise 3 and paste it right at the bottom here. Sorry. And then comment it out and run the program. So I get this result. Okay, actually it's not shared anymore. Let's put it private. Local. Oh, sorry, wrong place. Okay, so it's local 4. You can see that it's not shared, right? Because right now this x becomes private already. Okay, do you see there's something that is weird a little bit here? I declare x outside the pragma OMP parallel one time and initialize to 5 right over here. Next, I also declare another time with the same name, x. Is it okay? It looks like okay, right? And it works. Actually, it's okay. And this can be a problem because it is quite confusing. So the 2x has the same name, but even though they are the same name, they are two different variables. Okay, they are two different variables with the same name. Now, if you declare it inside here is valid with the same name, it's fine. But whenever you use it here, it will use the one within this block of code. The block of code is actually this block of code. Okay, within this braces. Okay, this is one block of code. So whatever x that I use here, including this string thing, will be using this x, not the outside x. Okay, it's the local or internal x. Now, what if, let's say I print the x again, but this time I print it outside. Let's run the program. Okay, you see local for 16 times, and then finally you see x is 5. It's no more 4. Okay? The reason is because when I get out from that code block, now I'm printing x, this x is the outside x, not the inside x. Is that clear? So the x is not overwritten. They don't replace one another. The 2x are two different values. Okay, they don't share. Right? But then when I print outside, I'm able to print the x which is outside. Now, how do I get the x from outside? Unfortunately, in C++, we cannot. We are not able to use the x outside the block. Okay? If you want to use, then you have to use a different name, x1 only. Then you are not overwriting the external or the global x. I should say external rather than global. Global is outside. Okay? Alright, another thing that you see here is this. You see when it gets printed out, it's only one time. Not multiple times, only one time. Okay, this is very clear because anything that is outside the prime OMP parallel, only a single thread that is running. Not multiple threads, only a single thread. Okay? Once it enters into the prime OMP parallel, that code block becomes parallel. That's why you see 16, depending on how many threads that you have. Okay? Now, how do you set how many threads? We will come to that later. You can set the number of threads to now. You can put 50, 60, 100, 100. But here, by default, 16. Okay? Okay, let's move on to the next one. I think the next one is the exercise already. Oh, sorry. The next one is the private. Actually, you can try out private. But this is dangerous. You can try that. You don't do this. Okay, private is another way, but private is slightly different. When you put private x, you make the outside x become private. But right now, if you put empty parallel, this is dangerous because everybody is trying to access the private value outside. Okay? How to use this private, I'll explain to you later. But for now, don't write like this. Okay? Although the private keyword is available here. We can make this x, which is outside, become private. But this is not the way to use it. Okay, but I'm going to skip this. If you want to try it, you can just copy this and then put it into exercise. Whatever else you can do, you can try it now. Just put it here. Exercise 4. But this is not advisable because we have race condition. Okay? If you want to run this, just copy and paste it. If you run, you will see this, but this is not the good idea because it is dangerous as what it says there. Okay? Although if you look at it, it looks okay. It's dangerous because it has what I call it, race condition. Okay, why race condition here is a problem. Okay, let's say for example, I have let's say a simple problem. I have a number of items. And I want the computer to count the number of items inside there. Okay? Of course, you can assign one thread to count each one of them, but it takes time because you have to go and count one by one, right? Okay? If you have a parallel computer, what you can do is you split them. Okay, you split them like this. Or maybe horizontal, but let's split it vertically. Then I give this one thread, I call it T, thread 0, to count this. Thread 1, count this. Thread 2, count this. Thread 3, count this. And so on and so forth. Okay? So I got multiple threads, and then each one of them will focus on one column, or maybe horizontal. It's up to you. Let's study it more. And what it does is, all of them will be executing at the same time. And thread 0 only focus on counting this only. So here 1, 2, 3, 4, 5, so 5. And thread 1 will be counting as well. 1, 2, 3, 4, 5. So it's 5 as well. This one 1, 2, 3, 4, 5, 6 maybe. And so it's so forth. Okay. One thing good about this, compared to single thread, is that everybody is counting at the same time, and they have less to do, right? And they have the sum, and then you have to sum them up together to the final total, right? Then you'll be faster, right? If let's say you got 10 threads, you'll be theoretically 10 times faster if you split the job evenly. 10 times faster, at least, at most. So, and then finally you got this subtotal, and then you sum them up, you get the final total. Okay? Now, suppose you don't do this subtotal. Everybody is sharing this final total. Let's call it final total, right? It's one variable. It's shared data. Okay? Now, initially it was 0, right? T0 compute is 5. Then you override this. So first you will take this 0 first, take 0 plus 5, it's 5, and then you will take this 5 and override. Right? Now next, let's say T2 finish and is 6. So you grab this 5 and then take 6, add it together, 11, and then you override it. Okay, that's 11. Now let's say this one is 7, 8, 7, 5, let's say. Okay? Now suppose this thread 3, okay, comes along and then read it, 11. But before it finish, T1 comes along, also read 11. Okay? And then this will add 8, this one will add 5. And then this one get 19, this one get 16. Okay? Now who is faster? Maybe this guy is faster, you override it, 19. And this guy comes along, override 16. Is it correct? Totally is wrong. This is race condition. Okay? That's why shared data is dangerous. That's why he's talking about dangerous. Now we don't see that because sometimes the result is good, okay, in order. But it can happen like this. Like for example, the first few times it was correct, but the last two was wrong. Why is it wrong? Because they are reading the stale number. Okay, and when they override it, they override with their own updated value, which is not correct, because they forget to actually wait for the others to finish first. So the whole idea is, if you want to fix this, you must make sure that only one person deal with this. Once it finished, complete it fully, then only the other can take over. Okay? If we can organize or synchronize it that way, then we can solve this problem. In fact, that is the solution to solve that. And how to do it, we will study later. Okay, just now I showed you how to split it, right? And we're going to use this idea to solve the problem in question number 2. Okay, let's look at question number 2. Which is this one. Okay, write a program that computes the numerical integration below. Mathematically, we know that, okay, it says that you know, but maybe you do not know. This equation here, especially this expression, when you integrate from 0 to 1, you get the value of pi. If you want to know what is the value of pi, you do this integration, you'll get the value of pi. Now, one thing about this pi is that the number is very, very long. Okay, let's look at the pi. Maybe it's not good one. So this is pi, and this is not the end yet. We can carry on. The number will never end, and this number is not the same. And it's very lengthy. Okay, you can carry on and on and on. Now, how do you find this number? One of the ways is actually to compute this. You integrate this, right? And then you can find this value here. Okay, this pi value. It's going to be very, very lengthy. If you want high precision, then you keep on compute the decimal points, right? So this is one way to compute pi. Okay. If you are able to integrate this using calculus, I believe all of you studied calculus before, right? Studied calculus? No. DCS. No calculus. No calculus in your first year. Mathematics calculus. Huh? STBM only. You're from STBM. Anybody here from STBM? Or STBM? Okay, if you study STBM also can, because I think we have calculus there as well. Okay, so we have integration. I believe you have seen it before, right? So integration means, what does integration means? Okay, here I explained a little bit because otherwise it's hard for you to actually run the program later on. The program is actually given down below here. That is to solve the problem at the top. But let me explain first. Yeah, I just ask whether you know calculus or not, because if you understand calculus, then it's easier to explain. Okay, the equation here is this function, not this function itself. Let's call it small f fx. This too is different. That capital F is the integration of it. This is small fx. Is 4 divided by 1 plus x squared. Okay, so this function. Now, if you plot this against this, let's say this is fx. Let's call it y. Y, and this is x, you see some kind of curve there, just like what you see. Something like that, right? So this equation describes this curve. If you plug in x into here, you get a value of this fx, which is y. Okay? So if you find x, you get the value there, then you plot. Find another x, you plot. Find another x, you plot. If you keep on doing that, you get a curve. Okay? Alright. Now, when you integrate this function. This is the fx. If we integrate from 0 to 1, this fx, small fx, dx. Alright? You're basically doing this. You are finding the area underneath it. Okay, so this is the area under the curve. That's curve. This area. Alright? So, but then of course, if you use calculus, if you know how to convert this, you will convert this integration of this function into another equation. And then you plug in these two values, you get the answer. But of course, that one you need to solve the function if you know how to do integration. But how do you tell a computer to do it? Unless the computer is AI, where it knows how to study this and do the integration for you. But before AI, we are able to solve this as well. But how does the computer do it? For any kind of function. Because any function, when you integrate, we have another different formula, right? If you come up with a formula, you just plug in the value, you find the result straight away. But here, computer does not know how to solve this. I mean, non-AI computer will not be able to solve this integration. He has to use another technique. And that technique is quite simple, and is first discovered, maybe explained by Newton. Okay? Newton lived in 17th century. So he said, if I were to compute this, I can chop it or slice it into thin slice, something like this. Slice it, slice it, slice it, slice it, right? And of course, this one looks like a curve. But this thin slice looks like a square strip. Just like what you see there. Isn't that square here? But there's some error there, right? There's some error there. Okay, some of them is, the error is quite big, some error is quite small. Okay. So you can see that this is a square, and it represents this. If you make this square even smaller, then the error will be even smaller, right? And that's why when you do the integration, you always say that this delta x is equal to 0. Okay, go to 0, as small as possible. That's why we get dx. Okay, we don't write this, but we write it. Okay, so this is the limit. The limit that you bring it to 0, and therefore you will get the most accurate as possible. Okay. All right. So we're going to use this idea. We're going to break it into slices, right, of certain size, and then we assume that this is a strip of a square, a perfect square. Now we can find the area of this square, right? What is the area? Is the delta x multiplied by the y. The y is this fx that we found. You put the x inside there, you find the y, you got the y, you take the y, you multiply by it, and you get the square, the area of this square. Right? And you repeat this for all. And then you sum them up together, what do you get? Basically you get the area underneath. It's just a rough estimation because you got some error there. Okay? Now in order to make it high precision, you make this delta x smaller. By making this delta x smaller, you have more strips, more of this to solve. Okay? Okay, let's look at how we solve it using a single thread. The program is here. Okay, by using this, you don't need to have only this function. It can be any function here. Okay, any function, and your computer using the same program is able to solve this problem. So using this simple way of solving, you can actually find all areas of any function. Okay, or the integrate any function. Okay, let's look at how we solve. First, you see num steps, 100,000. 100,000 means you chop it or slice it into 100,000 slices. Okay? Okay, so there is number of steps because why? Because you got 100,000 steps. Okay? And then you look at here, the step size is 1 over num steps. Why? Because the step size is delta x, is 0 to 1. Remember 0 to 1? Here is 0, here is 1. Right? And then you chop down into 100,000. Isn't that the same as 1 minus 0 divided by the number of steps? That will give you the small steps here, right? Right? So you get that. Next, what you do is you compute this function. Okay? And you put the x in. That means you put the x, each x inside here, and then you get the y, right? The y is actually fx. And then what you do is you take this y multiplied by this delta x, you got the area, and then you sum all together. So that is what is done inside this folder. First, you find the x, and then you substitute the x inside the fx. Okay, the fx is this, 4 divided by 1 plus x squared, x times x is x squared, and then you sum it. Okay, you keep on adding into one another. And you get the answer. Okay, now this one is a little bit different from what I explained here. You see that here, it doesn't multiply. Okay, by right, you should take this. This y is fx, right? Multiplied by the delta x, which is the step. Okay? So this fx is basically 4 divided by 1 plus square plus delta x, right? Okay? So let's multiply. But here you don't see any. Okay? Factors out is multiply outside here. Okay? So what it does is you see here, you take y and then you multiply with it. Let's say this one is y0, this one is y1, y2, y3. So you take y0 multiplied by delta x plus y1 multiplied by delta x plus y2 multiplied by delta x, and so on and so forth. But you see the delta x is the same delta x, right? You can factor it out. So you get y0 plus y1 plus y2 and so on and so forth. Okay? So what this for loop is doing is actually sum this y only, without multiplying yet. And you multiply where? You multiply here. Multiply outside. And why would you want to do that? The reason is because if you multiply first, then every of this track have to multiply. It takes extra time to multiply. Right? If you factor it out, you just add, you save the multiplication, and then you multiply one time on the outside. Only one time. You don't have to multiply so many times. So this is actually optimization to make sure that we don't waste our time multiplying inside here. Because the step size is the same. We can factor it out and we can multiply outside. So after you multiply, you get a pi value, and then you print it out. Okay, do you understand this? Understand? Okay. You need to understand it, because otherwise, when you try to optimize, you want to do parallel computing, then you find it harder because you don't understand what you're looking at. Okay? So once you understand, it's good. But let's look at this again. Just now I showed you how to count, right? And then I told you that we chop it down into a number of segments, and then you let each track process and count the number of items, right? Now we do the same thing. You see that it's chopped down into multiple strips here. So you can actually let the track to solve each block one by one. Okay. Now we got how many segments or how many strips here? We got 100,000. But remember, by default, we got only 16 threads. And 16 threads, if let's say we got 16 core, each thread is assigned to one core, then we can execute it in parallel. But maybe we don't have enough core, okay? Maybe we got only 8 cores, but it doesn't matter. Let's say we got only 16 threads equal to 16 cores. What we can do is this. We assign 16 cores or 16 threads to do this in parallel, okay? And then you move on to the next block. Do it in 16, another 16 in parallel, and you repeat that. So effectively, minimum, you get 16 times advantage, right? Performance gain is 16 times. Right? Because let's say you got 16 cores, so performance gain is 16. You cannot get more than that. Okay? Even though you got 100,000 there.
unless you got a GPU which has a lot more, maybe 1,000 cores inside there, which we have, then you can execute 1,000 at the same time. Okay? Then we get 1,000 times performance. Right? But in order to solve this, we got 16. We have to do it like what I mentioned. But it's still okay because we get performance gain which is better than one single core. Okay? Now how do we solve this? How do we write the program? First, you know that this must be computed inside OMP parallel, right? This one must be executed inside OMP parallel. But all the threads will come in, and then we'll see 0. Okay? And then you execute until num steps. Why? Because you start from state number 0 until the last state, which is 100,000. Okay? So that's why it's 1 until 100,000. And step increment is 1. This is for single core. The single core has to do every one of them, right? But if you want to do it in parallel, you have to do some changes here. Okay, let me give you an idea how to solve this. There are many ways, but this way is one of the ways. Okay, let's call this 0, 1, 2, 3, 4, 5, 6, and so on and so forth. Okay? First, when the threads come in, let's say the thread ID is 0. Okay? You can find this thread ID, right, by get thread num. OMP get thread num. We have shown you how to get the thread ID, right? So you try to find out his own thread ID and use this ID to find out which strip to do. Because you don't want thread number 1 to do strip number 0 again, right? Okay? So thread ID 0 focus on this 0. ID 1 will focus on the second one. And so on and so forth until 16. Okay? By doing that, now everybody will run on their own strips. Okay? They are not doing any other strip. Their own strips. Okay? And they can execute in parallel because all of them are 16. They can execute in parallel. Okay, when we move on to the next one, thread ID 0 is going to execute number 16. Thread ID 1 is going to execute 1, and the next one will be 17, right? It will not do 1 here, it will not do 2 here. Why? Because it's already done by the rest of the threads. It has to do the next 16. So starting from 16, 17, and ID 2 will do 2 and then 18. And this one, definitely you know is 32, this one is 33, this one is 34. Is it correct? So by doing that, now we can actually create block of segments and then we assign to this thread one by one. So you can see that thread ID will start from 0, and then you move on to 16, move on to 32, 64, so forth. And thread ID 1 start with 1, is 17, how much? 33, 65, and so on and so forth. Okay, but then what is the interval here, the difference? 16. How about the difference here? Also 16. So you know how much to increment here, right? It's always the same for all the threads. Okay, don't change this because we still want to solve the whole thing, right? We still have to solve the whole thing. But what do we start with? Is it still with 0? Are you sure? Start with 0?
ID.
Yes, you start with ID. See? Start with ID. ID 0 start with 0. ID 1 start with 1, not 0. Right? Okay? Is that clear? Okay. If you study this line here, because the other group asked me, why 0.5? Actually, you can remove this 0.5. Okay, it's 1 multiplied by the step. Now, what does this tell you? Let's look at 1 without the 0.5. Okay, this x here is basically this. When I compute my x, when I compute my fx, I need this x, right, in order to compute this value, you know? But then I have delta x in it. Okay? So the first one is 0. Okay, x is 0. And I put the value inside there. 0 squared. So that is for the x0. x0 means 0. How about x1? This one is x0. x1 is next to it. x1 is x0 plus delta x1. Is it correct? Next to it, right? And then I compute again x1, then I get 1 plus delta x squared, isn't it? How about the x2? x2 is basically x1 plus delta x, isn't it? x2 is actually x1 plus delta x. But x1 is already this number. This actually is 0 because we have that. So it's basically it's 2 delta x, isn't it? So you know, x3 is 3 delta x, x4 is 4 delta x. Is it correct? Yeah? Isn't that the same as this? 1, 2, 3 is this is delta x. Yeah? Okay, so you got one. Okay, now let's look at this 0.5. If you look at the square here, I say I start from 0, so I start from here. This is delta x, right? Somebody don't like it this way. They want it in the middle of this delta x. So you take 0.5 multiplied by delta x. You get in the middle. Okay? Actually, if let's say your delta x is very, very small, there's not much difference. You can remove that delta x. I mean, it's 0.5, it's not really important. Okay? But if your step is big, then this 0.5 is quite important because it can make a big difference. Okay? So you can try it. You can increase this a lot, and then you remove this, and then you put it, and you find out the answer. The answer is not very close. Okay? But then if this step is small, then if you remove and you add it, you get a different, the precision is higher if you put 0. Okay? So that is the only difference. Okay, what else that I need to tell you? I think nothing else. Okay, so right now, you need to solve this. Look at this here, and then you have to use OMP parallel to solve this. But there are some shared data, some private data, right? Some shared, some private. Okay, tell me which one is private, which one is shared? Non-step. Shared or private?
Shared.
Shared, okay. How about step? Shared, because it's the same, right? How about X?
Private.
Private. Okay, private, huh? Cannot be shared. How about pi?
Private.
Shared, because the final result you want to print must be shared. How about the sum?
Shared.
This one you have to be careful. Yes, you have to be private. Now, how do you do this? Remember just now when I draw earlier on, with the counting example, I draw like this, right? And then I tell you about subtotal, subtotal, which is 5, 5, 6, 7, and then the final total, remember? Now you have to do the same thing as well. This one we call subtotal, maybe you just call it sub-sum, and the final one you call sum. Okay? Now this one, you make it private, or maybe yeah, you can make it private. Okay, I give you options. Right? You can make it private, you can make it shared. Now, let's assume that this is private. And this one also private. Sorry, this one shared. So this one shared. This one is private. Why? Because when I'm counting here, I count my own private sum. Okay, I don't share with the rest, right? Because if I share, I get the problem that I showed you just now. Okay? Then finally, everybody has all these numbers laid out already. What you can do is you take that number, you sum them up, and then put it inside it. Now, the guy who actually do this, the final step is sum all of them up and put it here. That track would not have any race condition because there's only one thread that do this. Every thread is counting their own one, and there's one thread, finally, take all of them and then sum them up. Okay? How to do that? Remember, let's come back here. Sorry, my code here. Remember when I did this, when I create this exercise tree, anything that is inside this one parallel, you will have multiple threads running this. But this code here that is outside this block is only one thread that is running. Okay? That means when you do the for loop, it will be multiple threads that is executing their own code. But when you sum this up, you do it outside the block. Because you know that when you cover outside here, there's only one thread that is running. And you choose that thread to compute all this, sum them up, and then put it inside there. And then you print it out. Okay? Now, that is provided that you use that private. But maybe you do not know how to do that. Now I show to you another way. You can make this become shared. Okay? The reason is because of this. If you make this private, then the thread that is outside here cannot see the private data. How is the thread going to sum it for you? You cannot, right? Because this subsum is private to individual thread. Okay, the single thread outside needs to sum them up, right? But you cannot see because it's private to the thread. You cannot access it because it already made sure it's private, right? So you got problem. Of course, there is a way to actually solve that, but I'm not going to show you that. I'm going to show you a simpler way that you, up to the knowledge that we have learned just now. We can make this shared, but we make this subsum an array, which is basically this. And this will not have race condition. Why? Because thread 0 only focus on element of array of this subsum, array 0. Element 0 is array. Array got a number element, right? So element 0 of this subsum is for T0. T1 will be element 1, element 2, element 3. So even though you update here, you are not touching the rest, right? So you are able to update it without race condition. Okay? But because it's shared, now the single thread that is outside here can see it because it's shared. Everybody can see it. So when everybody finishes, you just take all these values, sum it up, and then put it into the sum and then print it. Okay? Or maybe you have to multiply with the step first. Take the sum, multiply with the step, and that will be the pi, and then you print out. Okay? You get the idea? Okay, I want you to try it. You got how long? You got 15 minutes, is it? Or maybe longer than that. What time we start? When you finish? We finish at 1:30, right? Okay, so you got 45 minutes. Okay, try it now. And let me know if you succeeded. Okay, before you try, let's run using single thread first. Okay, let's call this. I'm going to show you the single thread, and then of course the single thread code is already there. Just start placing it. And then you convert it into multiple thread. Okay, so the single thread will be find pi. Single, call it single thread as single. Okay, and then you find pi multiple with on. Okay, and the code will be this code. This code. Okay. That will be long num steps. 100,000. Yeah, and then double step. And we have integer I, double x pi sum, double x step. The step is 1.0 divided by non-step. Yeah, I changed slightly the program. I don't have the typecast here because I don't need the typecast. You can put the typecast by using the button. The reason is because I already put 1.0, so it knows that this number is a floating point. If this one is 1, then you have to do double that. Okay, because this is 1.0, so I don't have to do double. Then I have a for loop. For I equals to 0, I less than 1 step. This one is I plus plus, okay? Because we are doing single process, single call, single thread. And x equals to I plus 0.5 multiplied by steps. And then we do the sum. Make sure that you initialize the sum to 0, because here I just add it immediately. So sum 4.0 1 plus x multiplied by x. Here we don't have x squared, but we can do x multiplied by x in C, or C++. Okay? So that is all for this. Okay, and then pi equals to sum multiplied by step. So that is the final part. And then here is printf. The result. So let's see what the result is. This one is pi is floating point. Oh yeah, another thing is you can print it like this. I'll show you another way of print. Show you another way of printing this. Okay, that's all for this. Okay, so find pi single. If I run this, if I run this program, you see this result. And this result is very close, right? Very close to the actual value. So the answer that it's quite close, right? 9.2. 9.2, this one is 9.3. I think this one. But actually it's quite misleading, and I think there is better precision than that. But it only prints so many 6 decimal points. Okay, print out from 6 decimal points. You can print more. You can ask printf to print more decimal points. Now I don't quite, because we are using C++, right? I don't prefer to use printf. I prefer to use cout. Here we use printf quite a lot. I want to use printout. In order to use printout, I need to include idle string. And I think all of you have learned this before, like idle string. Okay? And then I want to change the precision. The precision of my floating point. In order to do that, I need IO main. I think all of you have learned this before in C++, right? C++. Yeah. You can set the precision. Okay? Now the IO string, take note, it doesn't have a .h at the back, because C++ don't use the .h at the back. Okay? Only C use .h. So here don't have that. This one have .h. So coming down here, I don't want to use this printf. I want to use cout. One thing good about cout is this. I can throw in any object. It will recognize that object as floating point, integer, whatever I can print. Unlike here, if I want to print out pi is double, right? So I have to tell printf this is floating point. Please print out floating point. I can print out d, which is integer, but that one will not give me the correct answer. And C++ or C will not tell you that hey, this number is floating point. And you're asking me to print out integer. I can print out for you by print out garbage. Okay? So you can do silly things like this.
And sometimes you make mistake without you knowing. Then you say, how come the answer is like that, or you just believe the answer. So it can be quite tricky, and you will be misinformed. If you see out, you can just put I, and you can figure out that there is a floating point, and then you print out floating point. Okay? You will not print out as integer, because integer will give you a different value. Okay, you see some wavy line there. The reason is because you have to put SVD. Okay? But if you want to avoid writing this again and again, you can go up here using namespace. STD. You do like that, then you don't have to put STD in front. Okay? Now, I put I is, and then N1. Okay? This will give me something similar as what you see just now. Stop, so I will stop and run again. You give me the same as just now, with less precision this time. Less decimal points. Only 5 decimal points. So I want to change that to give me more decimal points. In order to do more decimal point, I have to set the precision. And I see out again, here I'm not going to print anything. I just want to configure everything now to give me a better precision. Okay, let's put it at 16. Sorry, long spelling there. Okay. Set precision, I can set the precision because I include this. If you see wavy line, you forget to put this IO manip. Okay, IO manipulation means. Make sure that you put it in here. Otherwise, you cannot use set precision. Okay, so I set the precision to 16 decimal points. Okay, when I run this, it will show me with better precision. Okay, so let's see if this is good result. And if it is, how good it is. 3.149 something until 8162. I think it's up to 5859, right? 5859. So it's up to this point. So the precision is up to this point. That's how precise it is. The rest at the back there is wrong. Okay, not precise enough. Okay, how many decimal points there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 precision. The precision is 10 decimal points. Okay, let's try to increase to 1 million. 1 million. Another 0 there. And run. It takes longer. Oops. So, not sure why. Run again and compute. And let's see. Let's see how precise. How good is this answer? Okay, now 58 is correct. 5897, and that one is 9, that one is 6. So this time has increased. The precision is up to this point. Okay, more digits right now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's 13 decimal points. Just now was 8 only, right? Oh, sorry, just now was 9, 10. Yeah, 10. So I got another 3 decimal points accuracy by increasing to 1 million. Yeah. Now let's try solve it using 1000. 1000. Oops. Okay. Good. This one is up to 592. 592. Up to here only. Because the rest are all not correct. Oh, sorry, 592, right? How many decimal points? 1, 2, 3, 4, 5, 6, 6 decimal points. Okay, if 1000, then this, and
we clearly see this, right? Because remember I mentioned to you this. If you look at the picture here, you can see that if you make this bigger, then you get more error there. Right? So the error is the one that you lose the precision. So you make it smaller, it's high precision. And now, if you increase the number of steps, then it's lower. Okay, so let's measure how fast and how slow. Okay, there's another function here. Get OFP time. Let's measure the time. You want to see how fast. Okay. Okay, this is actually get the time in second. Okay, so double. Let's call it W time. I'm not sure what you need to do. Just W time. Get the time at this moment, and then I get the time again, and I subtract with when I'm done with the computation. Done with the computation, and I get the time again, and I subtract with the previous time. I get the time before, I get the time now, and then subtract with the previous time. That will be the time difference needed to execute this, right? Then I print that time. Okay, let's run. Okay, the time taken, oh sorry. Is it double? Yeah, it's double. W time, sorry, no mistake. It's W time. Okay, the time taken is this much. It's 11 microseconds. It's pretty fast. 11 microseconds. This is 1,000, sorry, 1,000 steps. So 11 microseconds. Let's write down somewhere. Uh, 1,000 steps, 11 microseconds. Okay. Right. Let's increase to 100,000. 100,000 is 1,000. How many seconds there? 981. 981.5 microsecond. So it's a lot more. It's a lot more than this. Okay. Just now it was 11 microsecond, right now it's 981 microsecond. Okay, let's put 1 million. Okay, 1 million is 9 point. So it's a lot more this time. 9622.1 microsecond. 9,632 microsecond. Okay? So it's a lot more than previous. Actually 10 times more because it's only 10 times more here, right? You can see that this is 10 times less, this is 10 times more. So it's quite linear. Okay? So you can see if you increase this, you get better precision, but the time that is required is longer. That's why we want to use parallel computing to cut down the time. Okay, we want high precision, but we don't want to spend so much time. That's why parallel computing is important, right? Okay, parallel computing is the whole idea is to do that. Okay, we want to cut down. So try to improve this. Find out whether you can get, of course, theoretically is if let's say 16 cores. Is 16 times faster. That means divide by 16. But of course, you cannot get this theoretical value. You get maybe 3, 5, or 6 times faster. Okay, let's try it. Okay, in order to do that, you just copy and paste this and then do the changes. Okay, you do on your own. Let me know. You got half an hour now. Because I put 15 minutes to explain to you that. So let's call this multiple. I'll call it multi. Sorry. them side by side, run the single first, and run the multiple. Okay, to find out which one is faster, or whether you got a fast better result. Okay, you see something like this. We have the first one, and then there's, of course here there's not much difference there, because the second one, although it's multi, but then I use a single code, right? So you need to change it, and then you should see improvement here compared to the above. There's no much difference there because, as I said, it's running on the single code, right? So you try that, fix this, and check the answer. Make sure that the answer is the same. These two must be the same, exactly the same. Here must be improvement in time compared to the single. Okay? And what you need to change is something here, inside it. Maybe this one. Because this one is outside, right? You compute one time, you have to sum that one. Okay, use this idea, sum. Click as array 16, and then assign each ID to only update its own elements. And then one final thread is going to sum them up together. Okay, you go and get all of them, sum them up together, and multiply by the step. That will be I, and then print it out, and then print out the time. Okay. Okay, do that, and let me know if you succeed or you don't succeed. Keep check the answer. Sometimes you get very fast, but the answer is wrong. Okay? Okay, try it now. You got half an hour. If you want to save this and put it to your Google Drive or your thumb drive, the program has a lot of artifacts, and these artifacts are the executables and all that you don't need, right? So the file can be in megabytes, 100 megabytes, so it can be very large. Before you save, you do this, put in your assignment when you submit. You go to Build, Clean Solution, you click on this one. Clean the solution. Once it's clean, then right click, go to open folder file. Okay, then you get the program. This is the one that you want to zip. Okay, when you zip, you can see the size is very small. It's only 10 kilobytes. Okay? It's only 10 kilobytes. But if you don't clean the solution, this can be 100 megabytes. Because it has all the garbage inside. Okay? So first, before you do any zipping, go to Build, Clean Solution first. Okay, you click on Clean Solution, you clean everything. All the artifacts will be removed. Only your source code and your project file will be inside. Will be retained. Okay? Okay, do the change and let me know if you succeeded. Any question? Anybody has question?
No one has question?
No. Try to solve using parallel computing. By using the idea that I mentioned to you just now. Okay, you want to learn more about the OMP, you can actually go to this, the one that I showed you just now.
The website is given to you here. Okay, you go to the resources. Oops, sorry. Resources, tutorial articles, and you can download some of the exercises. You can try this at home. Okay, all the code is given there.
老师想把这个原本是 single 的放去array 里面，那个 array 啊，因为 array 就可以最多10个，然后它就10个一起算，然后再看它的速度跟这个聊快，然后
没有要跟
打一样
不乱。
因为我们这个老师只有一个了，它就一个 tray 在做，然后是我们做成12个，最多的 tray 在做，那你要放什么？是放就是一条交易。很奇怪，不知道对不对？是这个。
Okay, time's up already. Oh, yeah. Brandon Chow. Brandon Chow. Wrong class. Oh, sorry. Wrong. Cha Yin Yong. Chu Zizik. Zizik. Jia Zhenyi. Jin Jiaman. Jin Jiaman. Gan Wei Song. Burma Dashina. Sorry, Dashina. Wei Jackson Chan. Lao Yongjing. Li Shen Tai. Liu Wei Zhen. Lin Chia Yi. Lin Wei Han. An Chen Ho. Hui Shun. Kang Yu. Samyukta. Tan Chong Han. Tan Senji. Tan Su Yin. Tan Wen Tao. Yao. Wang Xin Yi. Yi Zhengjue. Yi Zhengjue. Zhengjue. Okay, did you get the answer? You should get the answer. So I showed you my multi-sum. Remember I mentioned about summing up. Here I use this technique here. Okay, so roughly when you solve a problem, the technique is something similar, but I'm solving different problem. Okay, so I try to sum up, and I know that I've got 16 thread, that's why I put 16 thread. Actually, it's not a good idea. Okay, and then when I summed it up, I summed up an 8-part sum. And finally outside, there's only one thread running. You take the part sum and sum it up and display the sum. Okay? So you get sum after it's useless. Sum is useless. Okay? So when I run my multi-sum, I get this answer. I think this one is correct. So if I run multiple times, I get the same solution. Yeah, so this is not the solution just now, but something like this when you do. Okay? Where you got a part sum and then you sum it up here and get the final answer. Okay? So based on this, you can roughly modify to solve the problem. Okay, we can go now because they don't be lost later. Sure. I'll see you later. Okay, if you want to save it, clean solution first. After you clean, go to practical, go to open folder in File Explorer, and this is the data project. It's called practical. We go up and zip it if you need to zip. Okay? Let's zip it. Yeah, then you can save it.